Good morning, students. Welcome back to physics class. We were discussing wave optics and we have already seen Huygens wave theory of light. We already saw the phenomenon of interference, and we saw that by Young's double slit experiment, which shows that light can show the phenomenon of interference, which is a characteristic property of waves. It confirms that light is a form of wave. And today we will see yet another phenomenon exhibited by light called diffraction. Diffraction also is a characteristic property of wave. So it further confirms that light is a form of wave. Let us see what is diffraction and how light shows diffraction. Here you can see the definition of diffraction of light and also few pictures. Let us see what is meant by diffraction of light. The bending of light into the geometrical shadow area when light passes along the edge of a sharp obstacle or while going through a narrow slit is called the diffraction of light. Look at this figure. Here you can see an opaque object and light is coming towards its edge. These red lines show rays of lights and this blue line show the wavefront which is always perpendicular to the direction of propagation of light. Now here, if light was not a wave, we expect that the light ray will pass and we won't see anything in this shadow region. What we will see will be a dark area here. But in practice, we don't see a complete dark area. We see some amount of light in this geometrical shadow region. This is because the light rays slightly bend to reach this geometrical shadow. This will be shown only by waves. So we know that light is also a form of wave. In this figure, you can see a narrow slit. This is actually narrow. This picture is magnified. Now, when rays of light enters through this slit, we expect that there will be nothing or darkness in these regions. But since light behaves like a wave, it bends towards the shadow region and we will see some bright colors or bright light in the shadow region. Here you can see a narrow opening of the door. So the space between this door and the wall will act as a narrow slit, and see the pattern of light or the shadow of light. Here we expect that if light was not a wave, if it was a stream of particles, we will see only one bright line. But light has the property of waves. That is why instead of one single line, we see many bright and dark fringes or lines. This is called diffraction. So this is naturally occurring diffraction. Another example of naturally occurring diffraction is shown here. Here you can see sunlight coming through narrow slits produced in between clouds. And here you can see that it's not one single bright light beam coming, but there are shades, slight shades of dark and bright fringes that are coming and are incident on the water body down. So this is an example for naturally occurring diffraction. Here you can see a picture. This is a diffraction pattern produced in a laboratory while light passes through a small round slit. Here you can see a central maximum or maximum intensity at the center where light rays come directly through the slit. And surrounding that slit, what we can see on the screen is bright and dark fringes. So here the bright and dark fringes are seen, and you can see that as we go away from the central brightness, the intensity reduces. So this is a diffraction pattern which we can see in lab. So what is diffraction? It is the bending of light into the geometrical shadow when light passes along the edge of a sharp object or obstacle, or while it goes through a narrow slit. Now let us learn more about diffraction. Diffraction can be classified into two: Fresnel class of diffraction and Fraunhofer class of diffraction. You are not going into the details of these classes of diffraction, but we will just have a look into what is called Fresnel class of diffraction and what is Fraunhofer class of diffraction. If the source or the screen or both are at finite distance from the aperture or obstacle causing diffraction, we call it a Fresnel class of diffraction. Aperture means a narrow slit. Now, in such cases, the wavefronts are spherical or cylindrical. Here in this figure, you can see a source of light, a point source of light. Therefore, the light rays are coming from that point source and the wavefronts are spherical in nature. Now, when these light rays pass through a narrow slit, the upcoming waves also have spherical wavefronts, and this is the screen. So here, the source and the screen both are at finite distance from the aperture or slit. So this is called a Fresnel class of diffraction. Now let us see what is a Fraunhofer class of diffraction. The source and the screen both are at infinite distance from the aperture or the obstacle causing diffraction. So if the source and the screen are at infinite distance from the obstacle or aperture, what will be the nature of the wavefront? The wavefronts will be plane. Here you can see in this figure the case where the source is at infinite distance. For example, sunlight. Sun is at infinite distance from us. So if we consider sunlight, we can assume that the light rays coming from the sun are parallel. Therefore, the wavefronts will be plane. And when this light passes through a slit, in order to get it on a screen, the rays of light will be parallel again. In order to get it on a screen, we may use a converging lens or a convex lens. So at the focus, all these parallel light rays will converge and we can get it on a screen. So this is an example for a Fraunhofer diffraction. Here, the source is at infinite distance. We have the screen here at finite distance, but we are converging the parallel beams of light with the lens. So what is Fresnel class of diffraction and what is Fraunhofer class of diffraction? You just need to know what is the difference between them. You need not go into the details. Now let us see in detail the diffraction of light at a single slit. Here I have taken the picture from your textbook. See here, there is a source of light. And this is a point source of light. So we know that the light rays coming here will be going in all the directions and the wavefronts will be spherical. But in order to make the light rays parallel, you can either use sunlight or you can use a point source and use a lens. Now, if you keep the source of light at the focal length of this lens L1, we can get the light rays parallel, because when the light rays coming from a focus or principal focus of a lens passes through the lens, the light rays coming out will be parallel to each other. Here in your textbook, they have written the distance between the lens L1 and the aperture or the slit as F1. But what should be the focal length? The focal length should be the distance between the source and the lens. That's why I have cut that here and I have put here it as F1. So here you have the distance between the source and the lens L1 as the principal focus or the focal length of the convex lens. So the light rays coming from lens L1 will be parallel to each other. Now these parallel beams of light are made to incident on an aperture AB, aperture or slit AB having a width A. Now the light rays coming out of this single slit is made to fall on a screen. But to get them focused on the screen, we are using another lens L2. We know that when parallel beams of light passes through a lens, a convex lens, they get converged at the principal focus. So F2 is the focal length of lens L2. Here you can see the light rays which are coming from here parallel goes through the slit and they are focused on a screen here. Now if light were not wave, we will see only all the light rays focused on at a point O. But light shows diffraction, which means there is a bending of light ray when it passes through a narrow slit. Therefore, instead of focusing only at a point O, we can also see light at point O1 and maybe O2, O3, O4, etc. Here you can see the intensity of light plotted on the screen. Here at the center where maximum light goes, you will see high intensity or bright light or high amplitude shown like this. Now, it's not enough. In this geometrical shadow, it's not completely dark. You can see some intensity of light, not as bright as the central one, a lower intensity on both sides of this geometrical shadow. So here in the previous slide, we saw that the light ray at the center will be very bright, high intensity. But as we go away from the center, you can see light again with lesser intensity. So that's shown here. So this is light with high intensity, and as we move away from the center, there will be light again with lesser intensities. So here you have a source of light, and the light rays coming from the source is made parallel using lens L1, and these parallel light beams goes through a slit AB, and it is further pass through lens L2 so that we can focus it on a screen. And on the screen, what we can see is a central bright region or high intensity region and surrounded by lesser intensity of light. Now let us further look into this region. The path difference of two secondary waves emitted from the two ends A and B of the slit AB. So here you have light coming from the point A and point B. Consider this light ray which go and reach the point O1 on the slit, and the light ray that goes from B and reach the point O1. Here from this figure, you can see that this line AD is perpendicular to the line from B to this lens. So this is perpendicular, and so the path difference or the difference in distance traveled by the light coming from the point A and from the point B will be BD. So BD is the path difference. So look at this triangle ABD. This angle between AB and AD is theta. So this angle is theta. So if you look at this right triangle, we know that AB will be the hypotenuse because this angle D is 90 degree. So AB will be the hypotenuse, and for this angle theta, BD is the opposite side. So sine theta is equal to BD divided by AB, or BD is equal to AB sine theta. So the path difference BD is equal to AB sine theta. AB we know is the width of the slit, small a. So AB can be written as A. So BD is equal to A sine theta. So the path difference is equal to A sine theta. Now let us learn the condition for getting minimum intensity and maximum intensity. The condition to get minimum intensity of light is A sine theta is equal to n lambda. Here, if n is equal to 0, that refers to the central maximum. Now, if n is 1, it will be the first one. Okay, so here you have A sine theta n is equal to n lambda, and the condition for maximum is A sine theta n is equal to 2n plus 1 lambda by 2. We are not going to the derivation of this, but in order to remember this condition for diffraction, you can contrast it with the conditions for interference. For interference, the condition for maxima was A sine theta is equal to n lambda. Now it is the reverse for diffraction. The condition for minimum is A sine theta is equal to n lambda. And n is called the order, first, second, third, etc. If n is equal to 1, this will be the area. Now if n is equal to minus 1, it will refer to the down part. And if n is equal to 2, it will refer to this part. And if n is equal to minus 2, it will refer to this part, etc. So here, the condition for minimum and maximum is just the opposite of that we learned for interference. So remember that the condition for minimum for diffraction is A sine theta is equal to n lambda, and the condition for maximum is A sine theta is equal to 2n plus 1 into lambda by 2. What is lambda? Lambda is the wavelength of the light used. Now, let us see the difference between interference and diffraction. Here you can see the interference pattern and the diffraction pattern. What is the striking difference between them? Here in the interference pattern, you can see all these bright lights have the same intensity. Is it so for the diffraction? No. For diffraction pattern, there will be a central maximum and nearby intensities will be less. And all this maximum and minimum does not have the same width. So the central region is wider, and as you go away from the center, the width reduces. Let us see what are the differences between interference and diffraction. Interference of light is the result of interaction of light coming from two different wavefronts originating from the same source. Why do we consider two wavefronts originating from the same source? Because the light sources should be coherent. It is very difficult to get two independent coherent sources of light. And if you have any doubt regarding the interference of light and the coherent sources of light, you can see the class for that. I will give in the description below the link to that class. Then diffraction of light is the result of interaction of light coming from two different parts of the same source. We saw the light ray coming from point A and B of the same source or the same wavefront. This is caused by a single slit and this is caused by a double slit. Now fringes may or may not be of the same width. Mostly it will be of the same width as shown here. And for diffraction of light, fringes in a particular pattern are not of the same width. As you can see here, they are not of the same width. Now fringes in interference are of the same intensity. Looking into any part of this interference pattern, can you identify which one will be the central? No, because all of them have the same intensity. But looking into a diffraction pattern, you can definitely identify which is the central maximum, because fringes are of decreasing intensity. As we go away from the center, their intensity decreases. Now, the points of minimum intensity are perfectly dark, hence the contrast between the fringes are good. See, you have perfect dark and bright fringes for interference pattern, while the points of minimum intensity are uh, perfectly dark, but the intensity of bright fringes decreases. See, as you go away from the central bright fringe, the intensity decreases. Hence, comparatively less contrast among fringes. As we go away from the center, there will be comparatively less contrast among the fringes. So this is the difference between interference and diffraction. Now, diffraction can also be seen using another object called diffraction grating. We use this diffraction grating in our labs. So let us see what is a diffraction grating. A diffraction grating is a sheet having a large number of narrow slits of equal width lying side by side. So here you can see a diffraction grating in this figure. This is a diffraction grating. It's made of a single piece of glass, and the gratings are constructed by ruling or lining or scratching equidistant parallel lines on a glass surface with a fine diamond point. So with a fine diamond point on a piece of glass, scratches are made. Parallel lines or scratches are made, and then you get the diffraction grating. Laboratory gratings contain about 10,000 lines per centimeter. So these lines are placed very close to each other. In 1 centimeter width, there will be around 10,000 lines. And width of a slit. Slit is the region where there is no line. If you take a piece of glass and if you scratch that, what happens? The scratch part will be opaque. The light cannot pass through. But the distance between two scratches will be transparent. So that distance between two scratches will act as slit, allowing the light to pass through. And the width of that slit, that is the distance between two scratches, is about 10 raised to minus 4 centimeter. So with a width of each 10 raised to minus 4 centimeter, there will be scratches or lines made with a fine diamond point on a small piece of glass. Now, the distance between the beginning of one slit to the beginning of the next slit is called the grating constant, which means you get the starting of a slit. Then after the slit, there will be a line or a scratch. And at the end of that scratch, the next slit or the transparent region begins. So the distance between the beginning of one slit to the beginning of the next slit is called the grating constant. So this consists of a slit and a line. If the width of each slit is A, letter A, and the width of each line is B, they need not be equal. Then the grating constant D is equal to A plus B. A is the width of the slit or the transparent region between two lines, and B is the width of that line or the scratch. So grating constant is equal to A plus B. That will be a constant for a given diffraction grating. Now, how can we find the number of lines per unit length of a grating? The number of lines per unit length of a grating is equal to 1 by D. So it is represented by N. So I hope you understood what is a diffraction grating. Here you can see white light from a source which is passed through a single slit so that we get a narrow beam of white light. And when this narrow beam of white light is incident on a diffraction grating, what we see on the screen is this. In the middle, you will see maximum light passing through or white light. And to both sides, the light splits into its component colors. See, here you can see from violet, indigo, blue, green, yellow, orange, red, whipjaw on both sides. So when white light is incident on a diffraction grating, this is the pattern we observe. In the center, most of the white light will go and they will not split apart. We will see the full white light in the center, and on both sides you can see the component colors. Now let us see more about the diffraction caused by a grating. Here you can see two diffraction patterns caused by a grating. The above one is when we use a green source of light, a single color. So here you can see a central maximum, and here you can see some low intensity, another maximum, then some low intensity in the shadow region, another maximum like that. But the intensity of this central maximum is maximum, and the intensity reduces as we go to both sides. Now, instead of a single color, or instead of a monochromatic wave, if we use a white light, the central one will be white, and then you can see the light ray split into its component colors. See, this is called the central maximum, where n is equal to 0. And here you can see another one. This is the zeroth order. This is called the first order, where n is equal to 1 on one side and when n is equal to 1 on the other side. And here again you can see another color split. This is another spectrum of white light which you can see. This is called the second order. N is equal to 2. So this is the second order. So here you can see the central maximum. Then these two are the first order, and these two are the second order. Here with very less or faint intensity, you can see the third order. See, starting from blue to red, from blue to red. So this is the pattern we observe when light passes through a diffraction grating. If it is monochromatic light, this is the pattern, and if it is white light, this is the pattern. Here, let us again see this diagram which is taken from your textbook. Here, this is the diffraction grating. AB is the slit or the transparent region. BC is the line or the scratched or opaque region. Again, CD is the transparent or the slit. So the width of the slit or the transparent region is A, and the width of the scratch or line, the opaque region, is B. So what will be the grating constant? It will be A plus B, or represented by D. D is equal to A plus B. Now consider two light rays which comes from the point A and B. We know that the light ray go from A through E, and it is focused on a screen using a convex lens, and it reaches the point B, P, here on the screen. And another light ray consider coming from C, which goes to the point G and then goes to the point P. So what is the path difference between the light ray comes from the point A and point C? If you draw a perpendicular from A to the CG, which reaches CG at point M, this is a perpendicular. So the path difference between the light ray that goes from point A and Also, the one goes from point C will be Cm. So Cm, if you consider the triangle ABCM, means ACM, this triangle, this angle is theta. AC will be the hypotenuse, CM will be the opposite side. So sine theta will be equal to CM by AB. Therefore, we can get that CM, that is the path difference, is equal to AC sine theta. Or AC, you know, is the grating constant, which is A plus B. So A plus B sine theta, which is equal to D sine theta. So the condition for maxima is equal to d sine theta is equal to n lambda. And the condition for minima is equal to d sine theta is equal to 2n plus 1 lambda by 2. Now this is similar to that we learned for interference. So you just have to learn this formula by comparison. For interference, the condition for maxima is a sine theta is equal to n lambda, and the condition for minima is equal to a sine theta is equal to 2n plus 1 lambda by 2. Now for diffraction, it will be the reverse. Condition for minima will be equal to a sine theta equal to n lambda, and the condition for maxima will be equal to a sine theta is equal to 2n plus 1 lambda by 2. Now, when it comes to grating, the formula again changes. It follows the rule for interference. So we are not going to the derivation, but you have to remember how it goes. For interference and diffraction grating, it's same, it's similar. For interference, you have to consider the width A, or the distance between the two slits A. Here it is the diffraction constant, that's all, but the conditions are same. But for diffraction, it's the reverse. So that's all I would like to explain. In this class, we have seen what is diffraction, how diffraction occurs, and we have learned the condition for maxima and minima. For diffraction, we have compared interference and diffraction, and we have also seen how diffraction occurs in a diffraction grating. I hope you understood this lesson, and in the next lesson we will be learning a new phenomenon of light called polarization. So until I see you in the next class, bye bye. Take care and see you in the next class. Stay safe, stay healthy.